Today I'm going to talk about regression, and I'm wondering if anybody here is there any person who doesn't know what is regression, for example? Have you ever heard about regression? Okay, good. So then I need to start from linear regression. So because I have repeated this for 2 times, so I thought maybe I can skip, and then otherwise I can go for it. So the problem of regression is one of the fundamental problems in principle in machine learning, and the term regression is not very new. It's very common as a known name in statistics, and the idea is that when you want to predict something, you learn a function which is called a regressor, and then this is called regression. So for example, you have a function that you have set of input and then you want to predict an output. Sometimes in engineering this is called curve fitting, sometimes it's called function approximation, but classically in statistics it's called regression. So then there are different kind of regressors depending on the functions you are using. You have linear regression, and then later we talk about nonlinear regression. For example, these neural networks and deep neural networks, if you nowadays hear about them, are nonlinear regression. So, and as I said last week, I think one of the fundamental problems of, one of the key contributions, let's say, in machine learning is this idea of least square method, which changes the game. And I will talk about this quickly, and then after that I will show you what is linear regression, and then we go to nonlinear regression. So, as unfortunately, this week also I need to talk a bit theory. I promise you next week will be more applications. So this is a schedule. It's online also. So next week we will talk about an application that I developed in real estate market in Switzerland, and there we talk about random forest. Then next week we talk about how to use this machine learning in city environment and urban environments. So I show you two applications, and then I will show you also what is self-organizing maps, and then later we need a bit of theory again. We talk about deep autoencoders and then PCA and so on. I will show you with some toy examples like today. And then next week, I think also a bit, but these are very fundamental things. And then the rest are just applications. Like after that, we will talk about one case that I did, it's called in the field of urban morphology. Then I will show you together with Lucas one application of structural design, and then one application later on natural language processing, how to play with the text data set on a structured data set. And then also I have this papers. Before I have done these applications in collaboration, but this one, for example, this is ongoing application, and then I will show here you some of the recent papers. In learning physics here means that how to speed up computational fluid dynamics, how to speed up topology optimization, and this kind of things. And you're more than welcome to bring your own questions, and I have time. If you bring your own question, you can prepare it for one of these sessions, so it would be great. Because I know you don't have a background in machine learning, and also you might not be that interested in these techniques because you are interested in certain fields, but that's the case. We need to have a kind of compromise. So the regression problem, as I said, has this kind of names. Curve fitting in engineering, they call it curve fitting, or sometimes you have this field which is called inverse problem theorem, or in the field of systems identification, it's all about this kind of function approximations. But there is a combination of theory-based function approximation with the data, but when we talk about pure regression, it's just data. And then smoothing, you hear this kind of keywords. You can check them out easily with Wikipedia. You don't need to read a lot, so you know that if you're a good researcher, you just start with Wikipedia and then you go further, and you should be spiral. You can give a talk with Wikipedia, right? So the problem here visually is like this. You have a 2-dimensional environment, you have x, and here x is 1 dimension. It could be speed of your car, and this is the risk of accident or whatever. This could be speed of your robot, and this is the accuracy or the location that you want to reach. So, or this is some features of a house, you want to know the price of the house. Anything, right? So, as we discussed last week, classically we have theories for things, right? So, but when we are dealing with complex environment or local and temporal environments, like specific experiments, you don't have theory a priori. So then we need to learn this pure data. So as I said, the main concept here, in my opinion, which was introduced back in 1805 or maybe 1801, I guess, by Gauss and Legendre and some other people, is that imagine, just forget about the theory behind or mechanics of the system that you want to model. Just think about what observable factors you have and then what you want to achieve. And let's fit simply an imaginary function which has no meaning. So don't think about representation any longer, that this thing is representing the mechanics of your system. Just think you have a function here. We have a polynomial function like this. This is first degree polynomial. This is linear regression with one dimension. And then simply say, okay, if this is my function that I want to learn, how I should assess the quality of that. And this is the inversion. You just say, I create or come up with a measure of quality, or in statistics called goodness, I think, something like that. Fit, yeah, I don't remember exactly the term. How good is function is fitted to your data. And then you just try to minimize this error. So in principle, you don't think about theories and to build this based on the theory a model of the system. Here there is no model. And some people wrongly say this is a model, but it's not a model because it's not representational any longer. You just say these are observations, these are the sensors I have, and I put them together next to a target that I lit. So Y here is a target, and this is called squared residuals. And then the reason you have a square is that you have two sides of error, right? You don't want to cancel them out. So if you can minimize this, you get beta values, right? And these beta values are the values of your function. So that in principle, you can think about this as a kind of optimization problem. If you can optimize this function, you are done, because the decision variables are these betas. So these are some texts that you can read, and this historical moment that they use this for the first time is interesting to know. I just leave it here because we have a lot. So in principle, what we need to do is that we can visualize it like this first of all. So you have this data, and then I start with a and b here. So I'm trying to fit a function which is a plus bx or ax plus b, and then I can play with that. So if I change this slope, and this is the other one, goes up and down. So now think about it, that when this minimum happens when these distances are minimized. And there are lots of interpretation for that. For example, you can think about this kind of spring system, that different forces are pushing each other in different directions, and they're very greedy. These nodes, they want to have more contributions, so in principle they are trying to pull and push this line, and this optimization is all about that, right? So, or you can think about it like I would say is a kind of democratic voting system, that you want to contribute in your region, say, okay, I want to have this representative in the parliament, but you cannot change this structure easily because this is A and B, and then you have this linearity, and you can vote here. So it's not God-given setup, it's a voting system. It's a kind of democratic. But then, as we will see later, the whole machine learning is that, okay, what should be this f? Which kind of function give us the most freedom? Definitely linear regression works here, and then I will show you how to find the optimum, but then you will see that you have structural assumptions. So in order to find the optimum, for example, what you can, grid is not defined, okay, forget about it, we have it here, I don't want to. So in principle, one very naive way would be to do exhaustive search, which means that create a grid of A and B values, and for each pair, just check what is this R2 value, right? So if you do that, this is the space now. Because this R2 is a two-dimensional surface, you have a surface, right? So you can see this minimum is somewhere here. So you get this result. So this is, you can call it in terms of machine learning, a trained regressor, right? When you optimize the result, you get the weight vector, you just say now it's good to go, and then you can use it for other data set comes. So this is the regression in linear case. And also you can, I hope it doesn't crash, but it crashes. You can render it like this as a 3D space. This is the z value of these R2 functions that you here you have. If f is degree 1 linear regression polynomials. And the good news is that for this linear regression, you have closed form solution. So you don't need to do discrete search. You can easily calculate this based on linear algebra to find the answer. And also you can think about, you might think, what happens if you have higher degrees of polynomials? What happens? You might think that this becomes some kind of nonlinear regression, but it's not the case, because you can represent it like this. I cannot visualize it, but imagine if you have higher order, here you have order degree m, for example, polynomial function. You just multiply this x, one-dimensional x, to several times, m times, so you can build it like this. And now you can think about it like a linear regression with multiple variables. So the rest is the same, and I don't want you to learn this optimization, because I will show you it's easy to use. It's just to give you hints what is happening here. And now in principle, what you need to do is, based on scikit-learn, I don't know if you know scikit-learn, some of you know. Scikit-learn is an open source library written in Python, nicely organized and so on. And you have all the classical machine learning algorithms. They have amazing libraries with examples, and the best way to learn is after hearing these 10 minutes of regression. If you're interested in theories, there are lots of texts I can recommend. But if you really want to use it for your data set, just simply go to the regression page, and then there are lots of regression. And this is a lot of PhD students who work on these topics, like classical regression, and then what's the problem, let's solve it, and so on. And they're all easy to use. So if you get the concept, what's happening, then you can play with them. So you are opportunistic to any of them. You are not interested in necessarily to one tool set. So here, for example, this is the way you use it. You need to install it, and then you get, for example, this kind of toy data sets. Yeah, for example, this kind of patterns. And here I generate a set of random data points and with some noises and so on. And then now I want to play with the degree of the polynomials. Imagine now, every time that you said the polynomial degree 1, you find the optimum result, like this, and then you say, okay, now which degree I need. I hope it doesn't crash. So here is when you have degree 1, right? We don't do any grid search because it's a kind of inversion of a matrix. And if you change the degree, this is every time you see that what's happening, right? So in principle, you see that after several degree 10, you get almost good result. It learns from the function. And if you do it like this, it's hard. But here the problem is that the fun part is that it's explainable. So many people like this because it's explainable, whereas it's not good. But this becomes not easily explainable because you have x to the power 9, for example, or 8. So what do you want to talk about the power of a function and observation that you have? So it's meaningless, but it works. So this is a classical curve fitting. But then you realize that there are lots of limits to this. It's not like easy, because in many applications you cannot use this, otherwise there will no development. So I will just briefly talk about these limits. For example, after a certain threshold in polynomial degrees, they can't get better because they cancel off each other. And I was just reading, I'm not sure, but I think there are like open questions here. What happens if they have really high dimensional space? How many picks we will have? And then sometimes they cancel out each other. You will see that, for example, now let's play with that. Let's go to degree 33, and you see it has a very strange behavior. So in principle, when you increase the degree, it looks like that it gets better. It's getting better, but then gradually you see that it gets worse. So this is one of the known problems. If you have low dimensional, sometimes you don't get good result, and if it's very sensitive, right? So the second thing is that they suffer from the so-called curse of dimensionality, and that's important because when you, I will show you in a moment, when you multiply these vectors, these dimensions together, it creates a dimensionality. And the speed of increase in the number of dimensionality is exponential. And this is called curse of dimensionality. And then in principle, if you have a very large data in a vector space, your big data is a small data set. Because if you imagine if you have a 3-dimensional space, it's easy to fill this cube. But if this is a 10-dimensional space, you need a lot of observations to fill this space. So this is curse of dimensionality, and this is one of the fundamental problems you have in many applications. And I will show you what's the problem. And then also the training time increases exponentially because the dimensions are higher, so this matrix calculations doesn't work. And they always assume a functional relationship between variables. What if you have different regimes, not just always one continuous pattern? They cannot solve this kind of problem. And then, as I said, you have structural assumptions. So limits of regression, the first one is this. I think I showed you this, that the results doesn't get good. You had it visually here, and here you can go through the code. You can see that the error function goes down, but after a certain threshold, it gets worse. So that's very strange. It doesn't get better. But whereas, for example, later you will see that in the so-called deep neural network, always when you add more layers, you get better. It never gets worse if you have enough data. But here is not about that. It's just the limits of the code. And also, what is curse of dimensionality? Next week, I will in detail I show you this about this data which is in the case of real estate market. Imagine you want to use this. Next week, I show you how to use this in a real web application. But now, for now, imagine you have this kind of data set. It's not any longer one dimension to one dimension. You have, imagine, rents, which is your target. You want to predict the rent, and then you know zip codes, type of apartments, and then rooms, year of construction, and living space and location, right? So you have, in principle, 11 dimension, I guess. So let's see when we increase the number of these degrees of polynomials, what happens? Because they all get multiplied to each other, and then you have this problem of curse of dimensionality. So if you have degree 1, you have 11 dimensions. If you have degree 2, you have 66 dimensions, because you have all the combinations of the powers of this x's. You have 11 dimensions and they multiply to each other. And then if you have degree 3, 286, and then if you have degree 4 is 1000. So it's a very small problem. And now think about it, you want to use this regression for image classification. For example, you have a classification that you want to say, I like this picture, I don't like this picture. So output is always 2 dimensions, and the input is all the pixels. If your pixels are like, if your picture is, imagine, 100 by 100, you have 10,000 dimensions. And then if you go to degree 10 of polynomials, you want to get a good result, it doesn't work, simply. And that's why people are working theoretically in this field. These are these kind of fundamental problems. This is curse of dimensionality. And it's a very old problem in I think, optimization. So there are other problems, and then there are lots of extensions that I showed you here in scikit-learn, why there are lots of different names. I think it will be very confusing if I wanted to show you all of these details, minor contributions, but you should be aware of that. I mean, and the way you use it is just you have a certain question, and then you train these models against your data set or problem and see which one fits very well. And then in principle we have this notion of local polynomial regression. What happens if we can cluster our data and then locally we train these linear regressions? So in principle we have more freedom, because there is not one structure, is a kind of distributed setup, and it has a contribution. And then you have this notion of basis functions or different kind of kernels that we can use, but I don't go through it. And then in principle you have this general class of generalized linear models. I really suggest you test them. Go there, for example, and then they have a lot of toy examples with and then you just run them, and they have the same pattern. And this is the way you can really get it, how it works. Always you get this data set, and then you say, now this is my my model, fit it, and then you need to know how to measure the quality of your result. Then it's important to know some of the accuracy measure, and then you just need to build this pipeline. Then you just feed different models, and then gradually you understand why some of them doesn't work, some of them works. So for example, for my practical application, I always do that. I know what are the best methods, but I always start with simple ones. So it doesn't hurt. You just create a nice pipeline, and these are standard models. You just say linear regression, these. Later you will learn more methods, and that's different than focusing on one specific algorithm. So one important note I would like to highlight here, and I say a note for scientists who like to publish papers on based on scientific discoveries. It's very important. Be very careful if you want to use linear regression to explain something. These 4 different data sets have exactly the same regressor. So if you're listening in the media, for example, or publications, but I'm making fun of it, but this is happening in different ways. And sometimes this is called facts, right? But the thing is that if you talk about these coefficients, and then you say, I think if people run, this is the health outcome. If you don't run, this is the outcome. And if you want to say this is based on facts, you need always classically you need some coefficients. If you run this much, you get better this much. If your city is getting this size, your energy consumption is this size. It's always very interesting in the media. It's easy to publish in the popular magazines, for example. So this is happening, and it's not just this one. It could be anything. And this is exactly when you neglect this complexity. You just say, okay, now I use data-driven modeling, but I want to go to the shortcut and say, what is the coefficients? Because I want to sell my standards. You go to, and then you say, this is my standard for, I don't know, building energy consumption or building energy saving. They always ask you, okay, can you give us a table? If I do this, what's the outcome? And this is the result. And we really don't know. So I think it's important to be aware of that and act properly, I think, as a scientist, I think, because sometimes it's not the case. So next part is nonlinear regression, which is more interesting case. And this is a case when you don't know how to solve this equation. That's the main challenge, for example. In the previous example, I think I didn't show you because I was fast. Sorry for that. For example, this was a very simple example. Imagine you have this kind of observations, these pairs of observation, 1, 6, 2, 5, 3, 7, and so on. And then you want to fit this function. So if you write it down like this, you have a so-called overdetermined system. So in principle, if you have a linear regression with 2 variables, two parameters, you just need minimum 2 number of observations. And if you have degree 2, for example, you need 3. If you have degree, it's always one step ahead. But here, what we have is that, for example, you have 4 equations. Then in principle, we have more number of equations than the number of variables. So what we did here was that simply we wrote an equation, a function, which was the error function. We just calculated the differences. And then if you sum them up, it's like this function. And this is exactly the kind of surface. And then in this case, we showed you that you can optimize this analytically because it was an easy to solve. But most of the cases, these equations are not, or sometimes called loss functions, but it's important to know. These loss functions are not easy to optimize. And for example, if you have a direct optimization of a loss function, there is no iteration in the learning process. Everything is one shot. And as I said, I think there are many optimization people who really don't like, I guess, machine learning, because machine learning is always some kind of iterative algorithm, step. But then they say, what if I can optimize this function and I find a good solution for that easily? So that's it. So you just say, boom, this is a trained network. And if you don't know, for example, if you don't want to go to this iterative method, you can use this kind of genetic algorithms or the so-called evolutionary strategies. You can think about this space. In this case, I showed you, for example, there was two dimensions. You can select randomizing and then learn by some kind of genetic algorithms. This is also valid. But the most common way is an iterative method, which is called gradient descent. And this is extremely important. And this goes back to Newton also. This is very old. And the idea is that if you want to minimize a function, like f, and then you have a parametric setup, with like a1 to an, you need to iterate the values of these a's from any arbitrary initial points with this simple function. You need to know the partial derivatives of this function respect to that parameters, and then every time you go against the slope. And against the slope means, imagine you have this kind of function, y equals x2, right? When slope is positive, if you want to go to the minimum, you need to go to the opposite direction of the slope. When the slope is negative, you need to go again opposite to the slope. So we always push you toward the minimum. And that's the whole idea. And then you can see it like this. But then you will see that the most of the machine learning algorithms and the contributions are how to get these points. Because most of the applications or most of the loss functions, you don't know there is no global optimum. You just always find some local minimum or local optimum. So, but this is a way, and I think that's the whole machine learning. But then a lot of elaborations and details. So think about how we want to do it. Imagine you have this function. It is a three-dimensional function. You are interested in z, which is f of x and y, and this is a crazy and in principle useless function. Here is not necessarily a loss function, but we can show how we can optimize it. So, for example, imagine we know that the minimum value happens at x3 and y 0.5, and then if you visualize it, it has this kind of behavior, right? So the idea is that can I find a way that from any starting point, I go to somewhere here in this value, because this is where I get good networks. And think about this, if it's a space of possible networks, if you are training a neural network, if you are training a linear regression, nonlinear regression, whatever, this is the space of all possible neural networks. And if you have lower values, you always get better results. So what you need to do classically is that you need to calculate these partial derivatives, but you should not do that. This is already done. But we do it here for fun. Now if you have this function, from I think from high school mathematics, you should be able to calculate this partial derivatives respect to x. So for example here, now I define a gradient function of x, and this is the value. But the good news is that, again, a lot of contribution, open source. For example, these guys, Autograd, is a very cool thing. Whatever you write as a function in NumPy and Python, they can calculate for you what is the gradient function. So there is no problem. You just need to say, I want to know the gradient of f, argument is 0 or 1. So you have two arguments, right? And then, oops, okay, thank you. What was the problem? Okay, f, okay, I didn't want this f here again. So you see, we calculated this value for 2 and 3, and then this should be the same, right? So in principle, you don't need to worry about it. And if I want to be very fast, I say even you don't need this. For example, with TensorFlow, you just need to show what is the computational graph, and it calculates everything back. So, but it's important to have a feeling about it, I think. So the whole gradient is in here. It's just one loop. You just say while true. You start with any arbitrary point. I just say -4 and -3, and then you just have this function. This is this gradient function. It's right for any of them. And then you just say new x is the previous x, w0, minus alpha. Alpha is the steps, or you can call it learning rates, multiplied by the partial derivatives. That's it. And if you can do it, and then you just say until I get good results, don't stop. So I just run it here. So every time it should give me a lower result. It moves the points in the space of 2 dimensions, and then in principle you see that the function, which is in principle the loss function, is going to be smaller and smaller, right? Is minimizing this iteratively.
When you choose the step size?
It's just, these are meta parameters. The step size, the degree in the polynomials, all of these are called meta parameters, and these are always the things that you need to play with. So there's no way. Like the case of polynomial regression, you really don't know for each application what would be the parameters. It's
minimizing each step, or you just constantly?
Usually meta parameters means that parameters are those values that you want to minimize. But meta parameters are given by the user. It's always like that. And that's a philosophical problem, right? Always whatever you do is always a meta parameter. You cannot stop it. So here you see it doesn't find the local minimum, but it finds the global minimum, but it tells you that it starts from here, it moves to this point. So this method doesn't give you necessarily the global minimum, but it gives you the local, which is good. And if every time that you run it, it's different. And again, if you're interested, I'm not sure you can go and see there are lots of contribution on how to solve this problem. So if you want to know what's happening in machine learning society, this is this kind of optimization. How to speed up, and then for example there was a nice view here, which one is getting faster. Like for this kind of, it's exactly the same thing, which one goes to the global minimum faster. In my implementation even it doesn't go to global minimum, it goes always somewhere else. But yeah, this is very important, and there are lots of people working on this. So in principle this is nonlinear regression, and if I want to now switch to another way of talking about this is what I call computational graph. And think about now a linear regression as like this: w multiplied by x plus b. So this is a vector multiplied by a vector plus a scalar value, you get a value. This was the case. So you can think about it like a graph, like this. X comes, calculations, and then output. This is a linear regression. And if you say I want to have polynomial regression, this is the case. You calculate several features of x, still you are in this x side, input, and then here the arrows always are computations. This is the computation on each of these nodes. I just replicate them. So you need to do these kind of things for all of them. Then this is called polynomial regression. This was what I showed you before. And if I think about several of them in the row, because now it's just one function. So now you just say, why should it just one function? What if I have 10 functions? And then there are lots of strategies how to share the information together. But in principle, this is now same several x. Let's think about it, for example, with 1. And now instead of training one linear regression, you just say I want to train 5 of them, and I don't care. And then again, they sum up the results, and just think about it like this, that these are linear regressions. So linear regression is one node, and here you have multiple of them. And then now, just briefly, now you just say, what if, and you know that in this space you are always linear. You just say, what if I add another layer? What happens if I say, I don't think this directly produces the output, but what if this guy is the result of this step is an input of another step? Just for now for fun, but it's not for fun. And then you have this kind of networks. And this is a classical multi-layer perceptron, or now it's called deep learning because it has a depth. And then you can say, okay, I want to have more depth, so you have another layer. And then this whole process of automation of the calculation of gradient descent and so on. And here when you have depth, you need to know, there is another concept, I didn't need to go through it, it's called backpropagation. How to calculate, how to tell them what is the effect of this error that you have here to these parameters. Because it's not just one layer. You calculate everything. It's called forward pass, and then you just say this was what I calculated as this combination of whatever, and then it says no, it should be this. So you have this error, and this error function should be backpropagated back to all of these parameters, and there's a method to do that. And actually, this is gradient descent in different layers, but I just put the links here. But I don't think it's important because it becomes a bit complicated to explain in one session. But if you like, I would be very happy also to talk about it. So this is now, think about it as a kind of architectural way of looking at these neural networks things. And next week I will talk about random forest, for example. Then you will see that random forest is a one-layer neural network where these functions are with a certain conditions. In a way, they are randomized. In random forest, for example, you will see that you have linear regressors, but each of the regressors are looking at different factors. So here all the factors, in principle, when this x, or for example, when you have, for example, this, let's say, 6 of them. When you have 6 variables, and then all of them are being fed to each of these nodes, this is called fully connected layer, which means that this regressor single node is using all of these parameters. But then, depending on, you can randomize this, and then you create what is called random forest, for example. So, for example, you can think about a lot of other methods like support vector machines that I don't talk about this semester, but it's again the same thing. But it's very, I found it very extremely powerful if you think about machine learning like this, and it's actually like that nowadays with TensorFlow or a lot of software tools, that you really need to understand what's going on, and then you trust to the method that it finds out what is the parameter, and then you are just there. And then you will see that, for example, if, as I said, if you have a picture data set, for example, image, you have 10,000 dimensions, this structure doesn't work. There you need to know what is, for example, convolution. But then you have less space a smaller space for these high dimensional cases. So you have the notions of invariance and so on. But if you get this like that, in the beginning it's a bit strange, but you will think about it as like computational elements. And now recently, in this direction, recently they don't even call it deep learning, they call it differentiable programming. And if you remember last week I showed you a graph like this, and I said in the classical programming you write down these rules like switch, like this gated logical gates. But here you just leave it like random, and if this arrow, the weight of this arrow is 0, this means that there is no connection from this point to this regressor. So the model itself through data learns this structure, and this is the learning part. And I think this is the state of the art, I would say, the way that people think about machine learning. And then in principle you can think about multi-model data sets. For example, now what they do is that, for example, you can think about, in the context of computer vision, you have one side, you have a picture, one part of your data is a picture, is a kind of block, a picture input, a text. This is describe what is in the picture. And then you can feed this together and then learn this together, for example. So it's easy to use it. You just, for example, this is again, I just implemented this partially. I got it from this AutoGrad website, but even you don't need to do it, but it's really important if you know what's happening. For example, we can now think about that. For example, we want to build a network of, for example, in this case, you can read it like this: one input, then you have 3 hidden layers. Each of them have 8 regressor, let's call it, or 8 dimensions, 8, 8, 8, 1. So you literally go there and then you write this function to initialize these random parameters, and then it goes to all the layers, and then simply start with randomized weight vectors. It's like randomize these parameters of this polynomial regression, and then it wants to train them all together. And then you just write a function which is called prediction with parameters. You just simply say, and when you look at here, this is what I told you last week also. When you look at the here, is nothing more than a dot product. You have a vector, you do a dot product with the input and the vector. And dot product means like this geometrically. If you have this vector and this vector, dot product is 0. This means that this guy, when it's projected to this vector, has nothing to share. So they are orthogonal. In principle, information-wise, they have nothing to share information-wise. If it's like that, the dot product is 1. So it has most information. So you can think about this dot product as like that you learn some kind of vectors that are like sensors for a specific activity. Yeah, we will see this later in computer vision application. I show you. So everything is like that, and then this neural network, the forward pass, the so-called forward pass, is simply, where was it? To calculate this layers for each layer. And then the beautiful thing is that you can do it here in Python, is that you just take the input, feed the input to the first layer, the output of the first layer is the input of the next layer. You just do it in a loop, and then the output, and then you need to write a function which is the root square of error. For example, here I do it predictions minus target. This is the output is going from predictions, right? And then build a toy data sets here, and then you just say initialize my parameters, and this is arbitrary. Let's start with something else, for example 2 or 1, something like that, and then you build a network fully random, and every iteration it just calculates its gradients. So you see that this is the iterations, and then gradually it gets stuck, but it learns. Now I can generate some data sets. The red ones are predictions for the range of for the domain that I expected, and you see that it has a nice generalization, and you don't care any longer about these layers. And the fun part is that theoretically it's been proved that if you have only one hidden layer, you have a universal approximator for any function. But the question is that this curse of dimensionality. Of course you have this, but what if your input is 200,000 dimensions? Then you really need a large network, like horizontally, not vertically, not in this direction. And that's the limit why you will see later why we have depths, because with depths we create dimensionality. Without depths you only need to stack them in one direction, and they can't help any longer after a certain threshold. But in principle, I think there should, I don't know reference exactly which reference is that exactly, but you can, there people show this, that with only with one layer, hidden layer, you can approximate any function. And the good thing is that if you add more layers, it doesn't hurt if you have enough data. So it always gets better. It's not like the other polynomials that if you increase degree, it gets stuck somewhere. Here it always gets better, and it's fast. So now, for example, let's think about the previous functions. That here we wanted to optimize this function, but now imagine we are generating data in this kind of surface. It's the same. It's a bit harder. But oops. So I just created toy data set, and then let's think now. These are the tricks. For example, if you look at this function, it has some kind of exponential behaviors on the corners, and if you want to literally predict the dimension, the value itself, it gets really hard. But if you do logarithmic transformation, it gets extremely better. So these are the tricks you need to know over time if you want to use it. So now if we don't do logarithmic transformations, it's a bit slow. But if you have any question or comments, or meanwhile it's training, is it clear for you what's happening?
The network that you're saying you showed in the beginning, this regression, one function and one input, and then multiple inputs, one function would be
This
more for square, for example, right?
They're all based on, yeah,
more
one node is a polynomial, right? And then in principle you can think about that when you have higher degrees, I mean initially you can think you will add layer here, but as I showed you very fast, sorry. But here you see that when you have higher degree polynomials, in fact you don't change the function structure because you don't have new information. You can think about it as a multi-dimensional input because it's just the multiplication of the input itself with a linear regression again. So you don't change the structure, in fact, you just change the inputs.
Yes. But then if you add another function, how can I imagine it's a superposition at the end of many functions?
No.
If you go down now to the next one?
Yeah, I'll show you. The output of here is just always a number,
Yes,
right? So always you think about the output of each node is a number. So if you have this one, after this step, forget about previous step. Now you have 1, 2, 3, 4, 5, 6 numbers. So think about it as x again. So you just think about that this is the input to the next layer, right? It's always repetition. And these middle layers are extremely important because they later you will see that they're like channels of like they're classically like filters. You will see later that if you have, for example, let's do it. Maybe it's getting clear. Imagine if you have 4 classes, like, or let's call it 2 classes. I don't know. Dogs and cats. You will see that later, if you have these deep layers, these middle layers are extremely helpful because later you will see that only it's like linearization. You will see that like only these 2 gets super high values and these 2 gets very low values if it's cats, and if it's dog, these 3 layers are getting really high. And this is this is the part of learning, and it's called representation learning. You just learn the representation and you push the machine, and this again I'm going back to this least square method, because you just say I really don't know which parameters that I am observing are helpful, but in the middle layers you know that based on certain conditions these middle layers are learning everything. So that's the beautiful thing.
It's somewhat like a dimension reduction with a function.
Yes, the dimension reduction is a certain way if you say, for example, if I for no reason, for example, you just say I have 200,000 dimension here and I just want to get here 2 dimensions. But then you need to think about how do you want to evaluate it in dimensional reduction, because in dimensional reduction you don't have a target. So there you have this notion of autoencoders that I will show you in I think in 2 weeks. But if you do that, then in principle, for example, in these 2-dimensional layers, imagine if you have, for example, 2 and then it replicates itself, for example. This is called autoencoder. And then when you don't have target data set, like you don't have labeled data set, you just say this is the input, show me the input itself again. So reconstruct yourself, and the error is how different you are from the input, so you don't need to have the labels. And what happens here is that in the middle you only have 2 dimensions in principle. So if you can visualize it, for example, and if you visualize it, I will show you later in next week, you will see that, for example, they are separated. For example, if like classes of dog and cat, 1 dimension is activated for dog, the other one is activated for cat, for example. This is dimensional reduction. You take this dimension here, and that's it. And it's fully, in principle, we can call it unsupervised learning. Yeah. So now for this function, I hope it's done. Yeah, but it like somehow stuck somewhere. So now this is the reconstruction. What I do here is that this is the data set I have, is a kind of coarse-grained data set, samples from this surface. You train your network by that, and then you want to see how good you are in terms of generalization. I have more data set. And if you do it like this, it's not perfect, right? But then you will see that, maybe next week if you don't have time, with this logarithmic transformation, because you manage to somehow cancel out the effect of this exponential effect, you will get very good result, hopefully. Okay, we have a bit. So again, if you have questions. But now, don't get so confused about this structure, but think about which kind of applications that you have. You have this kind of questions, for example. I think I know because I know what you're doing in terms of your research. I can come up with questions, for example. But I think it would be great if you can come up with questions, for example, that what would be my output, what would be my inputs, for example, and in which context. And then later you will see it's much easier to learn this kind of abstract architecture in that context. But if you want to spend too much time now in learning what does this mean, it's a bit confusing. But if you trust me, and then just try it with your data set. Just try to generate or find some data set from somewhere in the internet, and then say, this is input, this is output, I want to test. And then try to make this pipeline. And then pipeline means that you should have a modular code, modular experimental setup, that you just say, let's start with linear regression. And then you will see that there is a curse of dimensionality. And then you just change it with the other generalized linear models that you had it like scikit-learn. And then later come up with this code, for example. And then try to understand this code with your data. Because you know the context, you are not lost. But if you don't know the context, and I bring my data set, and if you don't know the techniques, it's like completely confusing. But you should have a point like that you know. This is important. So now hopefully you get better results. Yeah, that's not good. Okay, if you try it later, you will see that it gets better. Or if you like, you can do it again. It depends on the initial condition. Let's play it, please. So in principle, I'm done unless you wait for these results. No, but it works. It works. It works very well. And there are lots of functions like that. And here you can visualize it. It's fun, but this function is useless. And for example, next week I will talk about a topic which is called overfitting, because no one asked here, and I didn't tell you, that what if you are just learning this for your training data, and what if your data is, and your test data later is completely different? Can you generalize it? Because the beautiful thing with the theories is that if you say, this is the theory, I don't care about the data, but here is always a trade-off. So then you need to think about overfitting. Overfitting means that you have very, very good results for your training data, but when you go to the new experiments, it doesn't work. So sometimes you should stop your models to be very good for your training data, and this is called some kind of regularization. And you will see that, for example, next week, this simple one-layer random forest works very well. And actually they win all of its competition. You just keep randomizing the vector. And there is a reason for that. So now look, this is better this time. Still not perfect, but this is the data set. This is the original data set. Now we have a higher resolution surface reconstruction. So in principle we can say that these neural networks got what was this system behind this. So this could be any process that you're playing with. Yeah. And then you can now use this without experiment, for example. If you have expensive experiments, but you know that it's not possible to have a lot, but by this you can generate a data-driven simulation environment, for example. This is possible. When you want to see what happens, for example, you can imagine this is the behavior of a kind of computational fluid dynamics for calculating the total energy consumptions of a building. So you have several parameters to come up. This is one building. You feed it to the system to tell you what is the energy consumption or energy efficiency of this building, but you cannot do this for all of them because they're expensive. So you just have few data sets. Here is a lot, yes, and then you just say with these few data sets, and in that case, for example, you have maybe 20 dimensions, different features. Can I generalize it? If you can generalize it, in principle, you have a so-called emulator. Then you don't need to simulate it. So, for example, now if you give me new data set, I can tell you with this quality that this is the energy efficiency of this building, for example, or something like that. And this is somehow it shows that it has some errors, and this is the way to see that this is a predicted true value and this is a predicted value, which is okay. I think it's 45 degrees. So I think, as I said several times, I think the majority of algorithms that we will see later and during the last 50 years or so, it's all about this architecture of computational graph, and which kind of operation we need to put in each layer. These are very important. And then the type of objective functions or loss functions, like for example when you don't have a label, or when your labels are categorical data. These are just small things, but these are also implemented. You just need to say, I like to have this, for example, log likelihood, or I want to use now I don't know, mean square error and so on. You just need to understand what is it, but you don't need to implement it. It's a kind of language, I would say. You just need to learn it. And then lots of techniques of optimization that I showed you, and then next week I think I will talk about this validation problem, which is a very important problem, and then overfitting. So I'm done, but if you have questions or comments, I could see that sometimes your faces were not so excited. So sorry for that, but it's okay. But just really, let's just try to run this code again when you have time. And I think if you don't spend time, we don't learn it. That's simple. You might learn some keywords, but it's not helpful. But if you start with this code and then try to contextualize it, to find one application that you know, I'm pretty sure in 6 months you can come up with a lot of new questions. And it's really helpful. Yeah. Okay, thank you.